so we're just.
Yeah, so when you're early for that, you don't complain about.
No, you just
We're not early
sit
for
there
that,
and
it's
like
8:30.
mentally prepare yourself for the quiz.
So you complain about math class after math class, like at the beginning of your next class?
Never complain about that.
No, we never
No,
complain
really.
about math class.
Really?
This
Yeah.
isn't that problematic.
He's like, I'm over there.
He's like, all right, bet.
I'm gonna like have to try to traumatize you guys now. Like,
You're trying to compare with like chem lecture and our labs.
Oh, yeah.
Like, there's just no comparison.
damn it. Okay, let me catch you guys in multi and then I'll show you.
Great.
Yeah, it's complicated. Okay. All right, so where are we? Last time. Maybe I should just like use pi in a confusing place. And like, no, I don't mean the actual pi. I just wanted to call it the symbol. Okay, that's great. Okay. Funny thing is, there's something in abstract algebra where they talk about projections, and they use pi as the name of the projecting function.
Isn't that just wrong? Just
Right, so pi, you think of it as a function, so you can talk about pi of x, and it's like a function that projects something.
I don't like that.
So yeah, eventually the math people start messing with you like that too. They just use random symbols all over the place. Like, why do you use that? So funny. Also, sometimes they use the number 1 as a variable. It represents like the something that you call the identity element of a group. They might just write the number 1, but it's not the actual number 1. It just represents a certain element of this set. Yeah. Okay. Last time, we started talking about concavity, right? And I again want to emphasize that this is really talking about the shape of something. So I don't want you to think about this in terms of, it involves the second derivative, but it doesn't involve talking about something like increasing or decreasing. It talks about the shape of something. Basically whether you're shaped like this or you're shaped like that, right? And this was called concave up like a cup. This shape is called concave down like a frown. I told you all the things about concave up last time, so let's talk about concave down. Sort of deal with the same treatment there. So that is said to be concave down in the region if its tangent lines are always above in that region. So a function can have the kind of property that if you were to sketch, let me just talk about or that. If you were to sketch the tangent lines, pick a bunch of points in this region and sketch the tangent lines, you'll realize the tangent lines are always above the curve. Similarly here. And this shows that if you look at this, notice that this is a very steep positive curve. It's still positive slope, but less steep, so it's a smaller positive number. Eventually you can imagine that it might hit 0. You'll realize that the slopes are decreasing over time. That means the values of f prime are decreasing. And of course that means the second derivative is negative. You spoke about a function decreasing means its derivative is negative. And so if the derivative is increasing, that must mean the derivative of the derivative is negative, which gives us the second derivative. So this leads to again, f is continuous, differentiable, and f is concave down if and only if its second derivative is negative. And this also, again, has a mnemonic. Concave down like a frown. Right, so you really want to get it through your head that when you're talking about concavity, you're talking about the shape of something. You're not really talking about whether it's moving up or whether it's moving down, because either case can happen. You're talking about how it's shaped while it's moving up or while it's moving down. So if you're bending out like this, if you're bending in a way that it kind of looks like a frown, you say you're concave down, right? So concave down means your second derivative is negative. Right? So you're down, frown, you feel negative, concave down. Down like a frown. So that's concavity. It's a very important feature of a graph that we would often care about. And I'll just mention some examples a little bit later of why we would tend to care about this shape. Right? Because you're like, okay, that's a shape, cool. We can talk about it in terms of the second derivative. Why do we care? I'll tell you in a little bit, but beyond that, I want to talk about another thing just before that. Well, I want to talk about a couple things before that. So this leads to something that's called the concavity test. And it's pretty much analogous to the first derivative test, except this one uses the second derivative. And so find the intervals of concavity. A continuous differentiable function f 1. Find f double prime 2. Where f double prime is 0 or undefined. So basically it's like you're finding the critical points of the derivative. And 3. Test and conclude according to, again, so you would again start to plot things on a number line. Right, so let's say this is a value for which the second derivative is 0, or perhaps undefined. Pick a number to its left and to its right. And you're going to test it now in the second derivative. And in the event that your second derivative is positive, what that means is that your shape is concave up. And if what you get that your second derivative is negative, what that would mean is that your shape is concave down. So you're not talking about increasing or decreasing, you're just talking about the shape of your curve. How is it bending, sort of? So positive second derivative implies concave up, which I'll often abbreviate with just CU, and negative second derivative would imply concave called that's called a concavity test. There's also something called a second derivative test, which, I don't know, in practice I've never really found a reason to use it. I'm pretty much telling you because, just for completeness, I guess. But I think if you're doing the first derivative test, which you're often going to be doing anyway, this is kind of superfluous. I will tell you, one reason why it might be useful to even tell you about this is that in multivariable calculus there is going to be another version of the second derivative test, which is pretty important for you to apply. And it's kind of analogous to this one a little bit. So if you happen to get there and you remember about this, you can kind of match up some parallels to it. But who knows, you might forget about this anyway. So the second derivative test says the following. It is actually a way to identify maximums and minimums. So again, you run the risk of thinking that the second derivative tells you about maximums and minimums, whereas I kind of want you to think about that in terms of the first derivative. So this helps you to identify maxes and mins. But when you see how it's applied, you understand, oh, that's why you do it. So again, suppose f is continuous, right? At least continuous on the region that you're considering. Then 1, if f prime of some value is 0 and f double prime at that value is positive, that tells you it would be a certain thing. And 2, if your first derivative is 0 and your second derivative, so you still need to know about the first derivative at least. Okay, so let's think about this. Our first derivative is 0 and our second derivative is positive. Would you say this is a maximum or a minimum? What would you guess? Well, second derivative positive means what?
Concave up.
Concave up like a cup, which means you're shaped like this, right?
It's going to reach a maximum.
Right? And so
Oh, I mean.
the point where your derivative is 0 means there's a horizontal tangent line. So this actually leads to a minimum. So if your first derivative is 0 but your second derivative is positive, that is a way to identify a minimum point. It doesn't identify the minimum point in the case where the first derivative is undefined. It's only if the first derivative is 0, then the sign of the second derivative can tell you about max or mins. Right? Because you know your function levels off at some point, and this says you're shaped like a smiley face while you're leveled off. You have to be a minimum. Similarly here, the second derivative negative means you're shaped like a frown. So you're passing through a point where the function levels off, you have a horizontal tangent line, but you're shaped like a frown. That would mean that you are a maximum. So this can also tell you about local maxes and local mins when you consider both derivatives together. First derivative is 0, meaning you have your curve is leveling off. This guy tells you you're a smiley face, that would have to be a minimum. If you're leveling off but you look like a frowny face, you have to be a maximum. But in Calc 1, I usually And the first derivative test is a little bit more robust because that can tell you about maxes and mins, even if your derivative isn't defined, like in the case where you have sharp corners or something like that. The first derivative test actually won't care. So those are just two conclusions. So based on concavity, we can talk about the concavity test, which talks about the shape of a graph in a certain region in terms of how it's bending. If it's bending like in a smiley face fashion, where our tangent lines are always below, or it's bending in a frowny face fashion, where the tangent lines are always above. Another thing I want to tell you about that the second derivative helps us find is something called an inflection point. Now, an inflection point of f is a point where f is continuous and it changes its concavity. Okay, so that's what an inflection point is. A point where you actually change your concavity, which means you could be concave down, you hit a point, and suddenly you switch to concave up, right? Or vice versa. You could be concave up, and you hit a point. After that point, you switch to concave down, right? Such a behavior is called an inflection. And the point where this occurs is called the inflection point. So let's do that. That's called an inflection point. So and you could switch from either concavity to either one. It's just that before this point, you're one concavity. After that point, you're another concavity. Kind of like the chemistry exam. You were one person going in, and afterwards, you're a different person coming out. You were a smiley face going in, you're a frowny face going. Okay. All right. Too much, too soon. I get it. Okay, let's go. So that's called an inflection point, right? It's a point where we switch concavity. Okay. And so you can switch either from concave up to concave down, or they don't really. I don't really think there's like a prefix that tells you when you're switching from a certain concavity to the other one. It's just a general term. You were either concave up, then switch to concave down, or you were concave down, then switch to concave up. Whenever that happens, we call this an inflection point. And we can use the concavity test to figure out when these occur. Okay, so remember, concavity is determined by the sign of your second derivative. So pretty much figuring out where that second derivative is 0 or undefined is going to be the first step, and then you just plug in points to the right and the left of that point is going to tell you if the sign's actually changed. Okay? So when these occur, so you're essentially So pretty much you know an inflection will happen if you have something like this. Here's a point where your second derivative is 0 or undefined. Your f is continuous though. And over here your second derivative is negative, while over here your second derivative is positive. Then this guy is what we call an inflection. or you can go vice versa. Here's a point where your second derivative is 0 or undefined. However, your original function is continuous. And let's say over here you're positive, but over here the second derivative is negative. Then this is what we call an inflection point. Otherwise, it's not. That's pretty much it. So, because this would mean here you were shaped like a frowny face, you pass through this point, now you're shaped like a smiley face. Versus here, you were a smiley face, you pass this point, now you're shaped like a frowny face. So if you were charting this one, it would look like this. And if you're charting this one, it would look like that. And again, it doesn't necessarily have to mean increasing or decreasing. I could have this behavior with an increasing function. Right? Here I was concave down, then I switched to concave up. Right? Concavity is really talking about the shape. And when at any point where the shape just switches from one concavity to the other, we call that an inflection point. Now, I'm going to talk about why do we care? Concavities and inflections. I'm not going to write this out, so I'm mostly going to describe verbally. So put it in your notes. Describe verbally. Consider these situations. So let's say here I was doing like this, then I did like that, versus here I was doing like this, then I was doing like that, versus here I was doing like this, then I was doing like that, versus here I was doing like this, like that. Basically, the interest comes from the interpretation of the function. So the curve itself is not, it's not good or bad. It doesn't really give you good or bad news. But if you put an interpretation on what the function is tracking, then that might give you good or bad news, and the kind of news that you would want to know about. Interpretation of the function. And so you could, so what would the above say if, let's look at two different examples. If the function represents, let's go back to that profit example. Let's say we're tracking the profit that I'm making from a certain business. Okay. Now, in both of these cases here, we're increasing. But I want you to appreciate that they are distinctly different in some very important ways. Even though both of them are increasing, but this one switches from concave up to concave down. This one switches from concave down to concave up. This switches from concave up to concave down. This one switches from concave down to concave up. Now, if you're increasing but you pass through an inflection point and your concavities change, it's going to mean something very different. So we saw that a concave up situation told you that the tangent lines are always below, but that also means that the tangent lines keep getting steeper and steeper. So basically what that means is in this situation, it's not just increasing. You get the notion that it's increasing faster and faster and faster, right? It's not increasing at a constant rate, it's increasing by more and more as time goes on. So you can talk about, oh, let's say I'm measuring weekly profit. This is talking about, oh, profits are good, we're increasing in revenue, and we're doing it faster and faster. So let's say, oh, our profits increase by $10 this week, they might increase by $100 the next week, and maybe even $10,000 the following week, right? It increases faster and faster over time, right? So when you're talking about concavity, you're not talking about increasing or decreasing, but you're talking about the rate of increasing or decreasing. And a concave up function tells you that if it's increasing faster and faster and faster. So here, this means business is good, business is great, and it's getting better and better and better. If you look at over this point though, it's still increasing, however, the tangent lines are actually getting less steep. So this means that, yeah, things are increasing, but they're increasing slower and slower and slower, right? So maybe this week we're ahead by $1,000, but the following week we're only ahead by 500. Then the following week we're ahead by 100, right? We're still ahead, right? Things aren't bad, but they're kind of not great either, right? This kind of tells us maybe something is coming, maybe there's a problem somewhere that it hasn't caught up to us fully yet, but it's probably on the horizon somewhere, something is going on. So here you can say, business is good, but we should probably be looking for inefficiency somewhere. Here it's like, nothing to complain about. Everything is great, right? Here it's like, yeah, things are good, you know, we're paying all our bills, we're not behind on anything, but I kind of feel like there's a slowdown happening. And then, why the inflection point would be important is you figuring out when someone tries to say, okay, so business is good, but it's not as good as it could be. I feel like it wasn't always this way. I feel like we were doing a lot better at some point. Maybe something happened, there was some inefficiency introduced, maybe we hired some guy who's just not doing his job, or maybe something happened, right? Things aren't as good as they used to be. And if you wanted to figure out what that thing is, that's where you're going to look, because that's where the change happened. You can like, oh yeah, business was great, getting better and better, but you know, there came a point where things started to turn around. The inflection point is going to be the place that identifies that behavior, okay? So, increasing faster and faster, and then this is like, it's increasing, but it's increasing slower and slower. And that might suggest a lot of things to you that are a little bit more nuanced than just saying increasing, right? So someone who isn't into nuance, they would look at these situations and they see the same thing. Oh, we're increasing, business is good. They won't realize that there's something on the horizon that's probably going to hit you pretty soon. Versus here, yeah, business is good, it was getting slower and slower. Oh, something happened. Now, you know, what happened there? Was it, oh, we started a new advertising campaign? Did we reach out to a community that we didn't reach out to before? Did we get a new CEO? Right? There's something that happened at that point that made things go from good to great, right? The inflection point is what you're going to want to find, because that's going to tell you, oh, maybe that's, whatever happened around here, maybe we need more of that thing, right? As opposed to here you're losing money and you're losing it pretty fast. However, you're kind of slowing down. So it probably tells you, oh, things are starting to look up. They're bad now, but there's reason for optimism. As opposed to over here, things are bad and they're getting worse and worse over time. Like, we are bleeding money and we're bleeding more and more. We're pretty much gonna bleed out pretty soon if something doesn't happen very quickly. Whereas over here, the opposite is kind of true. We're really bad before, getting worse and worse. Oh, at this point, something changed. We're still kind of in the red, but we're kind of seeing the light at the end of the tunnel, okay? So there are some nuances that are happening here, and the nuances are, the inflection points, you can think of them as the harbinger of the news, that you can either have optimism or pessimism in a certain situation. It's a level of optimism or pessimism that you couldn't have had just by talking about increasing or decreasing. Right? So if you thought of this function as profit, business is great. Now it's just good. What happened? Right? Oh, business is good, could be better, oh, now it's great. What happened, right? So that's what the concavities would indicate, and the inflection point indicates when the change happened. Now you can imagine looking at these same graphs and say something like f of x represents now there's a very different interpretation, an entirely different motivation, okay? So now if you're tracking the size of a brain tumor, this will take on a whole other interpretation of literally life and death proportions probably, okay? So this is saying it's increasing faster and faster. Okay, we hit a point where you're still kind of in a bad situation. It's increasing, but it's actually not increasing as rapidly. Whatever happened at this point is kind of slowing the tumor down, right? Versus here, maybe it's just your situation just got exacerbated, or we did something that really put things in a worse situation. Versus these situations would be good. So in terms of profit, this is good, this is bad. In terms of a brain tumor, this is bad, this is good. But you can talk about the nuances of the situation, and you can kind of talk about is what's occurring making things better or worse, okay? And you can do that with a lot more nuance than you could have just talking about whether something's moving up or down, right? Because it doesn't tell you the full story all the time. Sometimes you need more information, and especially if you are trying to plan for something, or you're trying to figure out what you should be doing more of, what you should be doing less of, the concavity of a graph is a very important piece of information. So that's kind of why we would care. So looking at a particular curve, which is going to be pretty dry in a calculus class, because that's exactly how I'm going to phrase the question to you. Here's a function, find the concavity, blah, blah, blah. You might not care at this point, but it's not because there's nothing to care about, it's just because we're not giving you an interpretation in a calc class. I just want you to know how to do the calculations, and the interpretation comes later when you try to apply what I'm showing you. So that being said, I think I did all the theory for this section that I wanted to do. Let's actually probably just jump into some, I actually want to summarize everything, and then we'll jump into some examples. So we've been talking a lot about various derivatives. Let's kind of put it all together. So we are going to do topics where you kind of need to be able to identify different features very quickly, and you need to know where to find them. And so I really want you to have a very good understanding of what kind of functions help with what situation. So here, let's talk about the different kinds of functions. Let's talk about what they tell us. And hopefully I'll have enough space here. Let's talk about how they tell us. Okay. So in the grand scheme of things, sometimes we're just going to have some function that we've developed or we're given, and we want to analyze that function. So we can be given a function f of x, right? Now what does the original function tell you about? Especially as it relates to graphs, but probably in general. What would something like that tell you about? What information does f of x give you? What would you say? Like, what would you be looking for that you would look at the original function?
The position, the location.
Yeah, location. Position points on the graph. So if you're looking for a coordinate on your graph, you would use the original function. How would you figure that out? Well, you plug in the input. Plug in x into y equals f of x. Then the coordinate x comma y is your location or your position or the point on the graph. So even to start, we haven't really spoken about this, but it should probably be obvious. So you can start to talk about it in terms of the physics relationship in terms of motion. You can think of this as your position function, which in the physics context, we usually use the variable s for that. Okay, so that's what the original function would tell us about. What about the derivative? What information can the derivative tell us about? Okay. So the first derivative can tell you the important things, can tell you about when you're increasing, can talk about when you're decreasing. It can talk about when you hit maximums, can talk about when you hit minimums. Okay? So if you're in a situation where you don't care about the location, but you care about where are things getting larger and larger, where are they getting smaller and smaller, is there a maximum or a minimum somewhere? Well, the first derivative is the function you would look for at. You would not look at the original function in general. You would only look at the original function if once you find the x-coordinate where there's a max and you want the location where that is, then you look to the original to find the location. But originally, if you're looking for any one of these features, the first derivative is going to be the go-to guide. And how would the first derivative tell you about this information? Well, the first derivative test. Right? Pretty much you're going to do a chart, and you can, around some x value, you can see, oh, if you're increasing then decreasing, that's a maximum. And if you're decreasing then increasing, that's a minimum, right? As an example, assuming your function is continuous at the point x, etc. Right? So if you're looking for increasing or decreasing, or where max and mins occur, you should be looking at the first derivative. And how you would figure out where these things are happening, the first derivative test is the process. In the physics example, this is what gives you what we call the velocity function, the rate of change of distance. Sometimes, think of this literally as position. Sometimes you'll think of this literally as your velocity. We've also discussed the second derivative. And this guy tells you about concavity, whether you're concave up or concave down. And it also tells you about inflections. And a good way to do that, in my opinion, is the concavity test. For the most part, I find the second derivative test useless for a Calculus 1 class. Some people like it. You might like it and you can use it. I'm not going to complain, but personally I don't really find need to use it. Once you do the first derivative test, you figure out the max and mins anyway. So we can talk about something like, okay, over here we can be concave up, or that concave down, switching to concave up, and that will tell me this is an inflection. As long as our function is continuous there, or we can do vice versa, concave up, concave down, that's an inflection. So we can actually do the concavity test. So this should really have a good understanding of what the different functions tell us, right? So the original function would tell us about location, about points on a graph. The derivative would tell us about whether we're increasing or decreasing and where maximums and minimums occur. The second derivative, which in a physics context is sometimes the acceleration, that guy is what you would look at if you're talking about concavity. So if someone tells you, oh, it's increasing, how is it increasing? Faster and faster or slower and slower? When that's your question, concavity is what you're searching for. The second derivative is the go-to guy. If you want to know about inflections, when we switch concavity from concave up to concave down, the second derivative is also your guy. You just do the concavity test. All right, so that's kind of summarizing this section. Now let's do some examples. Which will probably spill over into next time, which is fine because what we learned here we'll actually need to use in the next few sections. So we're going to be covering curve sketching pretty soon, and we'll need to be able to analyze a graph like this to be able to sketch it in. So find the intercepts. Local extrema. Intervals of increasing, decreasing, intervals of concavity, and inflections of the following. Or of course they exist. You can have a function that doesn't have any of these features. And here are the examples. So you need to be able to identify these features. So there will be a section called curve sketching, and usually the problem statement is going to be something similar to this, except it will have and sketch the graph at the end. Right? So it'll give you a function, it'll say, find all this stuff, sketch the graph, indicate them on your graph. So that's kind of where we're going here. But the first step is to find all these important features where they happen. So let's look at the first one. So here we would say for intercepts. So for the x-intercept, you set y equals 0, solve for x. Get no solution. The y-intercept, you would set x equals 0, solve for y. Also no solution because you can't plug in x equals 0. So there are no intercepts. Next thing we want is local extrema and intervals of increasing and decreasing. Now, because we're looking for this, all of that comes from the first derivative. So I know when I'm answering this part of the question, I'm going to need the first derivative. So what I'm going to do, so now increasing, decreasing, max, min, that's another section. I'm going to take care of all 4 of those items by looking at the first derivative. And the first derivative here is going to be minus 2 over x cubed. This would mean x equals 0 is the only critical point. So I would put that on a number line, test it in the first derivative. 0 is here. I would plug in a number over here, say minus 1. Plug in a number over here, say 1. Pick any random number, just make it easy. So don't pick like, oh, 137 over 54. Why would you pick that? Pick 1, it's a very easy number. Pick a number that you can plug in very easily into your function. Some numbers are so annoying that even if you're plugging them into a calculator, it's annoying. Just pick something easy. Here, plug 1 into here, you will get a negative number, right? So you'll get a negative. If you plug minus 1 in here, you'll actually get a positive number. So it tells you you're increasing over here and you're decreasing over here. So what can you say about the point 0? No, it's not. It's nothing because it actually doesn't exist. 0 is not on the graph, right? So it would be a max if your function was continuous there, but it's not. Okay? So you should, even though the problem didn't state it, you should kind of consider the domain in your mind while you're doing a problem. Good? Therefore, I can say at this point, I can tell you where my function is increasing, decreasing. So I can say it's increasing on minus infinity to 0. It's decreasing on 0 to infinity. There's a max, well, there's none. As for mins, none. So that's the second part of this. The next part talks about concavity and inflections. So I know when I'm looking for that, I will consider the second derivative. And the second derivative is going to be 6 over x to the 4th. So now you know that the critical point for that guy is again x equals 0. So here I have this interval. I'm testing 0 into the second derivative because I care about these things. So pick a random number over here, say minus 1, random number over here, say 1. It turns out they both give you positive in this case, but that means something else. This means concave up, right? So not increasing, it talks about shape. This means concave up. So it turns out that this graph is concave up everywhere. So there's no inflections. There wouldn't be anyway because we're not actually continuous at this point. And so that would be it. So you are concave up on minus infinity to 0, union 0 to infinity. You are concave down nowhere. And as far inflection points, you have none. And by the way, we actually know what that graph looks like, we should. So we can actually know, that's why that's the first example, it's the easy one. You can actually see that you're concave up here, you're also concave up here. You notice that you're increasing here, you're decreasing here, and clearly there's no max or min to this function. next time we'll look at the others, right? They're not as obvious. But we'll stop there for now. See you guys next